Video, we're going to go back to property 1 of our laws of limits, and we're going to prove this, but this time we're going to let the c in the property be infinity rather than a real number constant. These properties that we have are actually true whether you're taking limits as you approach a real number or approach infinity or negative infinity. And so we're going to prove this, but we have to modify the proof a little bit. It follows very similar to that proof before, but a little bit different because the definition is a little bit different when we're talking about limits as we approach infinity. So remember this definition for a real number L and a function f, we say the limit as x goes to infinity of f of x is the limit L. If and only if for every real number epsilon there exists a real number n, this time not delta, but n greater than 0, such that if x is greater than n, then L minus epsilon is less than f of x, which is less than L plus epsilon. So here's the proof of property 1. Property 1 was that the limit of the sum is the sum of the limits, basically. So we're given that the limit as x goes to infinity of f of x equals L, and the limit as x goes to infinity of g of x equals m. Suppose we're given any value of epsilon, any positive value. Now, epsilon 1 then could be epsilon over 2, which is also a positive number. So corresponding to epsilon 1, there is an n1 that goes with this function f, so that this happens. Since the limit as x goes to infinity of f of x is L, by our definition that we just read, there exists some n1 greater than 0 such that if x is greater than n1, then L minus epsilon over 2, L minus epsilon 1, which is epsilon over 2, is less than f of x, which is less than L plus epsilon over 2. And similarly, since g of x has this limit m as x goes to infinity, by definition there's another n, say n2 greater than 0, such that if x is greater than n2, then g is close to m, specifically between m minus epsilon over 2 and m plus epsilon over 2. So in both cases we're using this new epsilon, which is the original epsilon divided by 2, finding the corresponding n's. Now we let our n, I should say n, be the maximum of n1 and n2, and then suppose that x is greater than n. Well, if that's the case, then of course x is greater than n, which is in turn greater than n1, so x is greater than n1, so we get this equation, this inequality true here. And similarly, x is greater than n, which is in turn greater than n2. Okay, so we get this second inequality true. So we have both of these inequalities right here true. We add them together. This part of the proof is exactly like the proof when we were approaching a constant. If you remember back to that proof, we used the epsilon over 2. We found the deltas that we needed. In this case, we're finding n's that we need to make these equations true, and add up the corresponding parts. If you got two compound inequalities like this, if you add the smaller parts here, add the middle parts, and add the larger parts, you get those in the same order. And of course, this tells us that f plus g is between L plus m minus epsilon and L plus m plus epsilon for any epsilon that we started with up here. And so by definition, the limit as x goes to infinity of f of x plus g of x is the limit of f plus the limit of g, which is L plus m. And that concludes our proof. This little black box means we've finished our proof. We've shown what we have set out to prove. So we can make similar modifications to the proofs above to prove the remaining limit laws when c is infinity or minus infinity. I'm not going to go through all the details of those proofs, but you get the basic, hopefully you get the basic idea of what's going on there.